In this video, we are going to go over how to create a finite element model that resembles a wing box structure. Here is the final result that we expect to have towards the end of the video. If we look at this finite element model, we see what it's composed of. Here we have maybe the skin on the exterior. Here in the middle, we can consider that the rib of the wing. Here are these beam or stiffeners. These can represent the stringers in the wing. And then one thing I don't have in this model, I don't have a spar. So maybe during this exercise, we'll go ahead and add our spar in the interior of this wing. Now, there is a lot to cover here. This video is meant for Patran users. If you're new to Patran, this video is for you. Now, there are a few tools we are going to be using today that's worth summarizing. Number one, we are going to be using MSC Apex to build the mesh and the geometry. So MSC Apex would be this tool. Most of these tools are free. MSC Apex and Patran are free as long as you are a student. Google Student Edition Patran, fill out the forum, and then they'll go ahead and set you up with some access to the software. The post-processor web app is also free. That would be this tool. This tool is used to look at the results. So towards the end of this video, we're going to be looking at quantities like displacement, stresses, failure indices, beam stresses, and things like that. So that's coming towards the end of the video. And then towards the very end, we're going to do a very simple composite laminate optimization. We just want to set up maybe weight minimization by adjusting the thicknesses of the plies or the layers. Okay then, so let's go ahead and get started. So let me go ahead and close this tool. And let's go ahead and get started in Apex. So we'll go ahead and enter the sketching tool. So that would be this button here on the top right. Let's go ahead and click that and click this rectangular button. So we want to build a rib in the ZY plane. So let's go ahead and do that now. Let's go ahead and build a 1 meter by 0.5 meter rectangle. So let's go ahead and zoom out a little. And maybe I zoomed in too much. And now we have a problem. Let me go ahead and redo this. So I press the escape key. So let me redo this. I'm running this on a virtual machine, so sometimes my virtual machine gets a little sluggish. So let me go ahead and redo this. So let's go ahead and click Sketcher, select one of the planes, you enter this grid. Let me zoom out a little. So I'm using the scroll wheel to zoom out. And let's go ahead and click one time, then a second time. Here, let's make the height 0.5 meters. So 0.5 m. And then we'll make the width 1 meter, so 1 m. So now we need to create additional ribs. So how do we do this? Here on the right, there's a transform button. Click on that link or button. Click on this transform tool. And now here, click on this rib. And then click on this red axis. And now we're going to translate this rib by 1 meter. So type in 1m, enter. And then, so right now it's only translated the rib. Let me undo this. And this time, let me select the rib. Here on the right, click on copy. And redo the same thing. Click the red axis, type in 1 meter. And now I've created a duplicate of the rib. Now let me go ahead and do this again. So we're going to copy it, translate it by 2 meters. And then let's go ahead and do this again. We'll go ahead and do it 3 meters this time. And then we want one more rib here, so let's go ahead and do 4 meters. So there we have it, our 4 ribs, or 5 ribs actually. Now let me go ahead and do one thing. Let me go ahead and purposely make one of these ribs very large. When you build your geometry, not all of your geometry will be exactly how you want it. So I want to give you a scenario where you have an oddly shaped piece of geometry and then you need to edit it a little to get what you want. So let's go ahead and shrink this rib a little. Now here on the model display panel here on the left, let me go ahead and select these 3 interior ribs. So let's go ahead and right click and hide. And now for the remaining ribs, I'm going to create some additional surfaces. So here on the right, click on this tool, which is the geometry tool. Let me hover over that, make sure, oh, it's called the geometry edit tools. So click on that and click on fill surfaces. So that would be this tool, I believe, filler. And now here, this lightning bolt, click that. So when you have it on, it's yellow, but when it's off, it's blank. So click it so it's blank. And now click one edge and then click the other edge. And then these white lines are a preview of the surface you're creating. So let's go ahead and click the middle mouse button. And that's one of the faces we created. Now let's go ahead and do this again. So we'll click that edge and this edge. We get a preview with the white lines. Let's click the green checkbox here on the right, or click the middle mouse button or MMB. And then we'll just go ahead and repeat the process here and here. And then we'll go ahead and do this for the last surface. So depending on the version of Apex that you have, it might or may not create a solid geometry. So here on the left, we have a new solid geometry after we created these faces, but I don't want a solid. This is what you can do. You can select a face. So here, let me exit the filler tool. Let me jump into the split surfaces tool. Let me select this rib and let me delete it. So I press the delete key on the keyboard. It's asking me, if you delete this face, the solid is no longer solid. It's just surfaces. So say yes. And now I can see that this geometry is hollow. Let me go ahead and select the opposing rib. Select it. It's orange. Press delete on the keyboard and now it's gone. Let me escape or exit the split surfaces tool. Let me mark all these checkboxes in the model display panel. So now you can see that our ribs are inside. Now there's a problem with the ribs. Let me go ahead and throw a quick mesh on here. And maybe I'll use 0.2 meters for now. Let's go ahead and see how that looks. So this is 0.2 meters. The elements have a width of 2 meters. Now let me go ahead and mesh the interior rib. And let me use 0.4. So we have a problem. The rib has 3 elements, but the nodes at the interface are not aligned to each other. This is a problem for us. If we delete these 2 surfaces or meshes, let's go ahead and right click on this and delete. Go to the vertex edge drag tool. And you notice that the edges are red, green, or yellow. Red means that that edge is not connected to any other edges. So here on the right hand side, you can see that these edges are free, but these edges of the rib are also free. That's why we're getting this discontinuous mesh. What you could do is the following. You could just drag out the edge. So here I've dragged out this edge. And here I'm going to drag it back to this face. And now you can see that the edges are now yellow. That means that these 2 faces are combined. And now let me go ahead and show you what the new mesh looks like. So let's go ahead and create a new mesh, maybe 0.2 meters, and click on the surface. And now if you look at the nodes, you can see that the mesh and the nodes are aligned to each other. And that's because those edges are now yellow. They have common edges. And now if we look on the opposing side, let me go ahead and hide this other odd geometry. I think it was this one, right? So here, let's go ahead and do this again. So if I give this mesh size of 0.4, and if I mesh this rib, you can see this is not good. These 2 meshes are disconnected from each other. So you can either use vertex edge drag or you can use the stitch tool. So let me show you how to use the stitch tool. All you need to do is select the faces that you want to stitch, press the middle mouse button or click the green checkbox. And now you can see that the nodes on the meshes are aligned to each other. So it's one very important task that you have to consider. You have to carefully look at the colors of the edges. Are they red? Are they green? Or are they yellow? If they're red, in most cases, that's not good. If we look at this other surface, if you will, let's go ahead and mesh all of this. These two faces or surfaces are not connected. And you can tell by looking at the mesh, you can see that the nodes are not aligned to each other. So let's go ahead and work on how to connect both of these faces. So let's go ahead and delete that old mesh. And so if we look at this larger mesh or surface, this is what it looks like. Now we're going to go ahead and almost do like a cookie cutter. We're going to cut a square rectangular section in this face. So let's go ahead and show you how to do that. Let's go ahead and turn on the split surfaces tool. We're going to select this option, the split surface using surface plane. So this would be this option in the bottom right hand corner. Click this option, turn on both of the geometries. Now select this larger surface first, then click MMB or the middle mouse button. It turns purple. Next, select the face that's going to be used to split that first face. So let's go ahead and click the middle mouse button. Now if we look at the original face, it now has a split. And we can repeat the process. Select the face, select the next face, and now we have a second split. So let me repeat that a few more times. So select the face to modify, click the middle mouse button, it turns purple. And let me do that again because there's one step I missed. So again, enter the split surfaces tool, click this option, split surface using surface plane, left click on the face, it turns orange, click the middle mouse button, it turns purple. Select the faces that are going to be used to perform the split. So I've selected two faces by left clicking the faces. Click MMB or middle mouse button, and then this performs the split. So if we hide the larger surfaces, this is what it looks like now. Now, you want to delete maybe the larger face. How do you do this? Press the down arrow on the keyboard and make sure you've selected this option, faces. You can select this face and delete it. Let me undo that. Or you can select this larger face and delete that. So I've selected the face. It turns orange. Then I press delete and then it's deleted. Okay, now remember, you have to look at the colors of the edges. And here you can see that it's red. These two faces, these two geometries are not connected to each other at the red edges, so I have to fix this. You can use the vertex edge drag option. So here I've dragged the edge. I can move the edge so it's parallel with this face, and then this automatically performs the stitching. Or what I can do, I can click on stitch geometry, select all the faces I want to stitch, and now before it was red, and now the edges are yellow, meaning they're shared connected edges. And like before, I can go ahead and go to the split surfaces tool. I can select any lingering faces and delete that. So this looks aligned, or this looks like what I want at the end. Now, one thing I didn't do, and one thing you'll see throughout this video, I did not rehearse this video. So I'm going to make multiple mistakes, and you're going to see what I do to recover from these mistakes. Here, what I want to do is draw a big face or surface. And then let me clarify what I mean by surface, or I'll skip that definition for now. But first, let me create this very large surface or face. And let me reposition, or I'll leave it there. This face or surface represents the spar. Later on, I'm going to add some stringers, so let's go ahead and do this. Let's go ahead and maybe combine and stitch this geometry. Now, one quick comment here. Combining the edges only works if the geometry is in the same part. So here on the left, I now have two parts. In the first part, I have my wing structure, if you will, and then in the second part, I have this large face. If I try and stitch this geometry, it's not going to work because the geometry is not in the same parent. If you look here at the bottom left, I get an error saying the same thing. Hey, these geometries are not in the same parent. I cannot perform the stitching. Let me go ahead and move this face or surface to the first part. And now all the geometry is in one parent part. So let's go ahead and stitch this again. And now you can see that I have my, my common edges, if you will. Now, there's one challenge here. You can see that the outer surface for the spar is just too big. How do I fix this? So let's go ahead and work on fixing this. I'm going to enter the split surfaces tool, and I'm going to use the point method. So that would be this middle option. I'm going to left click on this surface, click the middle mouse button, and now it turns purple. I'm going to zoom in and I'm going to select these two vertices. Now be careful when you select. You might accidentally pick something that's behind the surface. So here you have all of these other objects here on the rear. So make sure you're selecting the right entity. And here I'll give you an example. Let me go ahead and move. You can see here it's selecting the edge behind this purple surface. I don't want that. So be careful when you select objects here. Here I want to select this vertex and then move it after. You can see this white line is giving you a preview of the split. Click the middle mouse button and now you've split that surface. Let's go ahead and do that to the other side. So let's go ahead and click that. We'll go ahead and select these 2 points. And then after I selected the 2 points, move the mouse away from the region so you can see the white line. Click the middle mouse button, and now we split that surface. Now what I can do is I can select this outer surface, and remember, press the down arrow on the keyboard. Make sure you've selected the faces option. Left click the face, and now press the delete key on the keyboard, and then it deletes the face. And now we have a spar here. Okay then, so let's go ahead and do the following. Let's go ahead and add a dummy material. Now later on, we're going to be using a composite. So for now, I'm just going to enter properties that are negligible at this point. So here I've added a dummy material. And now let's go ahead and add a thickness to these elements. So let's go ahead and type in 0.1 meters. Let's click assign. And we've assigned a thickness. Now let's go ahead and go to the surface mesher. Let's go ahead and try 0.4 meters for the element size. That's a little too large, so let's try 0.1 meters. And this is too many elements for this very simple example. So let's use maybe 0.2. Okay, this looks good. Here I'll leave it up to your judgment what element size to use, but I want to keep this example very simple, so that's why I'm using a very large element size. So after you've created the materials and the properties, you've assigned them to this mesh. Now it's time to go ahead and perform the analysis. And let me quickly summarize how I created the materials. Here on the right, I clicked on the sphere, which is the materials button. Here I've supplied a name, I've supplied the Young's modulus, the Poisson ratio, and the density. Then I click the sign, and then I select this piece of geometry. it's automatically assigned the material. If you look here at the bottom left, the status says assign material 1 to part 1. Then I have to specify what the thickness of the elements are. So here on the right, there's a sections button. Click on that. Specify the name, section 1. Specify the thickness, 0.1 meters or 3.94 inches. Click assign section. Select this piece of geometry. And then if you look at the bottom left, and now it says assign section 1 to part 1. So we're done. So now here in part 1, right click that and select place an analysis scene. And now we're getting some errors here, and here select normal modes and select run, or actually, yeah, let's click that. We have to click that button. Here it's performing a normal modes analysis, but I'm going to exit the tool after this. Here, what I want Apex to do is give me a new option. If you go here and click export BDF, this gives me an option to output the mesh to a bulk data file, which is a text file. Here, let me select meters, kilograms, seconds, newtons, Kelvin, I believe. But here we only care about the length, the force, and the mass. So we're dealing with meters, kilogram, and newtons. At this point, you need to decide what unit system you're going to be using throughout this entire exercise. Nastran is like a calculator. The calculator does not know what units you're working with. It's up to you to define what unit system you're working with. Here, we're making a decision. For the rest of this exercise, we're going to be dealing with meters, kilograms, and newtons. So that's what I've selected here. Let me go ahead and decide a location to save this bulk data file, and then click export. So if we go to that bulk data file, all the elements, all the nodes, all the materials, all of that's defined for me here in this bulk data file. So now what I'm going to do, let me go ahead and open Patran, and let me create a new directory here on my desktop. We're going to import that mesh. And the next thing we're going to do is the following. We're going to add some supports and some loads. So let's go ahead and do that real quick. So here is my Patran window. And then here, let me go ahead and save my Apex session. And one last thing. If you want to output the geometry, you can right click on the geometry and click export. Here, let's go ahead and select maybe a parasolid file type and click export. So let me go ahead and hide this. If you look at this geometry has been exported to this parasolid file. So you may or may not need this in the future, but here I wanted to show you how to export the geometry. Now let's go ahead and go back to Patran. Let's go ahead and click new database, and let's go ahead and select this database, or this directory. We'll call it model. And let's go ahead and import that bulk data file. So remember, we use Apex to output the mesh, and now we're using Patran to import that mesh. So here's our wing structure. There's some ribs and the spar. What you can do is click on this button here. So go to the home tab, click on this green button, and it's going to color the geometry for you. Now, personally, I don't like using green, and I actually have my own trick I have my own preferences to use for Patran, so I'm going to use my own preferences going forward. One thing you'll notice is that in the other Patran window it was green, but since I'm using my own preferences, the geometry should be orange or yellow, I believe. So let's go ahead and use my preferences. We'll import the bulk data file. Okay, this is a lot easier on the eyes. So here again, we're dealing with this wing structure. We have the skin, the ribs, and the spar. And now we need to add some boundary conditions to this. So we're going to jump to the loads and BCs tab. Here on the far left, there's a displacement and constraint box. Here we're going to say this is a fixed end. Here on the right, I've supplied the name. Under input data, we're going to say that the selected nodes, the first, second, and third degree of freedom are constrained or set to 0. The fourth, fifth, and sixth degrees of freedom, which are the rotations, those are constrained to 0 rotations. So we'll go ahead and supply a vector of zeros and another vector of zeros. Click OK. Now select application region. Now when you're working with Patran, there are a few things you can select. You can either select geometry or you can select FEM entities. Here there is no geometry, so if you try and select things, there's nothing to select. On the other hand, if you switch the option to FEM and you select objects, now you can select nodes. So here, set the select option to FEM. And now here on the far left, let's just go ahead and drag the mouse and select these nodes on the far left-hand side. Click Add. So here in the application region, we're assigning these constraints to the far left-hand nodes. Click OK and click Apply. So now you can see that my constraints are here designated with markers. Let's go ahead and change the background. So here under the display group, there's this button here, cycle background color. So this is changing the color. If you zoom in very carefully, it's telling you that degrees of freedom 1, 2, 3, 4, 5, and 6 are constrained. So let's go ahead and zoom out a little. And now what we need to do is apply our loads. So here I'm just going to do a very simple load, F1. I'm going to say we're going to apply the load downward in the Z direction. So here, maybe it's negative 1000 newtons. And here, select FEM, the node. Let's go ahead and select this node, click Add, OK, and Apply. And then I'm going to create a second load for a second subcase. So let's go ahead and click on Input. This time, I'm going to say 0, 0, and positive 1000. Here, instead of using zeros, I'm using blanks. So let's go ahead and select this node, click Add, OK, and Apply. So now these are the two loads that I'm working with. And now let's go ahead and do this. Let's turn on the model tree. And here under the load cases, let's go ahead and maybe modify the default load case. So here we have the support's been added, the two loads have been added. Okay, so that's okay for now. Let's go to analysis, click on entire model, and here we're going to call this test or model test run. For the solution type, we're going to perform a normal modes analysis. Click OK. For the subcases that are going to be considered, here I've deselected all the subcases. All the load cases have been removed from this analysis. Let me click and select the default load case, click OK, and click Apply. If you remember, here if we right click on the default load case and select Show, this shows you all the boundary conditions and loads for the default load case. So we've gone ahead and performed the analysis. Let's go ahead and import the HDF5 file. So here, click Analysis, the Analysis tab, click on HDF5, click Apply, and this will automatically import the H5 file that contains the results. Now, one thing you should always do is you should always inspect the F06 file for any user fatal messages. Always make sure that there are no user fatal messages in the F06 file. If you actually do find these messages, that means that there is an error and you have to fix that before you get results. Here, let's see. Or actually, I'll skip that. Okay then, so now that I've imported the results, let's go to the results tab. Let's click on fringe and deformation. Let's go ahead and look at the first natural frequency. So we'll go ahead and select the eigenvectors translational for both boxes. And then let's go ahead and select animate. That's a little too fast, so let's go ahead and slow down the speed bar. So here on the right hand side, there is a animation speed bar. You can slow that down however you like. And then let me go ahead and change the background color. So here in the blue, this is the original model, and then here in this rainbow color, if you will, this is the deformed shape, or it's actually not a deformed shape, it's a mode shape. So here we're just looking at the different mode shapes. The mode shapes are useful because they can tell us if our mesh is fully connected. If this is your first time using Nastran, the most common error you're going to get is a disconnected mesh. And now let me go ahead and show you an example of that with beams. So right now, if we go to the Home tab and we click on this button, Element Shrink, let me go ahead and change the background color. This will have to do. If we look at this different way of looking at the finite element model, you can see we only have 2D elements. There are no beam elements currently defined, so we have to add some beam elements. How do we do that? I'm going to show you two options. So let's go ahead and turn this off. So now we have the regular mesh. We're going to go to the geometry tab. We're going to select on the curve option and select the point option of creating our curves. So here at the top of the skin, I'm going to select these two nodes, if you will. So let's go ahead and select this first node, and you see it's turned orange. And then I'm going to select this other node here. And now it's hard to tell here, but there's actually a yellow curve here. If you go to the Home tab and you click on this button, Apply Erase Fem, it deletes, or it doesn't delete, it hides the entire mesh. So click this button off and on to show all the elements. Let me change the background color. Let me turn off the elements. And now this yellow curve is a geometry curve. I created this by selecting points on the mesh. So let me go ahead and do that. We have one curve. Let me create a second curve. So let's go ahead and select this node, and let's select this other node here. And let me hide the elements. And you can see we have two lines, if you will. So now what I can do, let's go ahead and mesh this. And before I do this, let me go ahead and turn on the lines again. Let me see how big the elements are. So here we're going to go to show node location distance. I'm going to select one element and then a second element. This is going to tell me how the size of the element. So it's 0.2. Here, if you look at the distance column, it tells you that the distance is 0.2. So I want my beam elements to be of length 0.2. So if I go back to the meshing tab, let me hide the elements. Let me go to the meshing tab and click on Meshers Curve. Here, let me select these two curves, and for global etch length, deselect automatic calculation. Here, we want to manually specify that the length of the beam elements are 0.2 meters and click Apply. And now, if you look here at the bottom left, there's some feedback. It tells you how many elements and how many nodes have been created. So always look here to see what was the last thing that's been done. Here again, it tells me I've created some beams on the curves with 42 nodes and 40 elements. Now here, if you go to the Home tab, click on Label. So that would be this L button. Turn on the Node ID button. So this tells me the node numbers for these beam elements. Click on this Element button. This tells you the element number for the beam elements. Now there's a problem here. Here, if we zoom in, we know this is node 2010 and 2011. Let me turn on the rest of the mesh. Let me zoom into the same location, node 2010 and 2011. But if you see here carefully, you can no longer tell what the node ID is. If we zoom out and zoom in here, we know this is node 1918 and this is node 1922. But here again, the node IDs are not legible. What's going on here? There are two nodes at the same position. There are two labels on top of each other. This is why you cannot read the label ID, because there are two labels, two nodes at the same location. Now, keep that in mind while I go through the rest of this exercise. Go to Tools, go to Beam Library. Here, let's go ahead and call this Beam Cross Section A. And let's go ahead and select the T section. Maybe we'll go ahead and make this 0.1 meters, 0.05 for the flange and the web, and we'll click apply. And then we'll click cancel to escape that tool. Let's go to properties. Here under properties, click on beam. So for the 1D properties, click on beam. That would be this orange button. Prop beam A. So here, this is where we combine everything together. We're going to combine a material. So click on this button here, select material 1, click on this cross section button, select this cross section, click OK, and now select application region. Here, remember, you can either select geometry or you can select finite element objects, so elements, nodes, things like that. Here, you need to select this button. Right now it's set to select surfaces or curves or other geometry objects, but I do not want to select curves or geometry objects. I want to select beam elements, so click this button, and now it turns orange or gold. Now I can scroll and select all the beam elements, and here you can kind of tell they're orange because you've selected them. Here I've selected elements 2093 through 2132. Click add, click OK, and click apply. And then bar orientation, right? So that's where one very important thing. What is the bar orientation? The bar orientation defines the y element axes of the beam cross section. So here I'm going to say make a orientation vector in the z direction, so 0, 0, 1. Click OK and click apply. And now if you go to the display load BC element properties, here in this new menu or panel, select this option, 3D full span plus offsets and equivalent cross section. Click apply. Now you can see what the beam cross section looks like. And here it might help to turn on the color. So this is what the beam elements look like that represent the stringers in this case. Here, I'm going to purposely leave the cross section very large, just so you can, or rather, I want to make this as simple as possible. So that's why I'm purposely leaving the stringers to have very large dimensions. Let me turn off this display. And now if I go back to this option, you can see carefully that we now have beam elements defined. So if you look carefully here on the left and right are the 2D elements, but now here in the middle, I have my beam elements defined. So these again are representing the stiffeners in this example. Now, remember, there are duplicate nodes here. So let's go ahead and turn on the node ID number again. There are duplicate nodes here. Look what happens if I try and perform a statics analysis. So let's go ahead and go to entire model. And let's go ahead and say model statics. So here we'll go and click on solution type, select linear static. We'll go ahead and select the default load case, which has all of our boundary conditions and loads. We'll click apply. Now remember, whenever you do an analysis, open the F06 file and look for this message. User fatal message. And there's nothing here. So let me go ahead and see what's going on here. Okay, so I think, I'm looking at the wrong F06 file. Here, I'm supposed to be looking at the model statics F06 file. So this is the results of the statics analysis. Let me search for user fatal message. And now I did get a user fatal message. User fatal message 9050. We have to fix this, so we'll fix this in a moment. If you go back to Patran, if you try to import the results, you get these errors now. And I know a lot of new users get these errors, so I want to clarify what's going on here. So these are the errors that we're getting. One is from Nastran, one is from Patran. So now let's go ahead and talk about what's going on here. Let me go back to entire model. Let me select the old test run. The old test run is set to normal modes. Now, if you're new to Nastran, if you're new to FEA, always perform a normal modes analysis first. Do not perform a statics analysis. Do not perform a transient analysis or a flutter analysis or some other type of analysis. You as a user, as a new user, your number one priority is to perform a normal modes analysis. I have to stress this a million times. So select normal modes first, click OK. Click apply to run this normal modes analysis, and then click yes for all these dialogues. And like before, this is the test run, so let's go ahead and look in this F06 file. Let's go ahead and search for any error messages, user fatal messages. There are none. This is a good analysis. Let's go back to Patran. Let's go ahead and import the results. And here on the bottom left, it says attach result file, which is good. Let me turn off the node IDs. So here in the toolbar, I'll deselect the nodes. And now let me go to the results section. Let me click on deformation. So here we only want to look at the shapes for now. Now we have various mode shapes, if you will. Let's go ahead and look at the first mode shape and select the eigenvector to display. And you'll see that we have a problem. Look at the beams. Let me animate the eigenvector for the beams. The beams are not connected to the rest of the model. That's a problem for us. The beams can either move up and down, left and right, in and out. They can rotate. They are not connected to the rest of the mesh. This error, user fatal message, this means that when you try and solve this equation, F equals Kx, K is does not exist, no solution, etc., etc. Here, what's going on is that since I don't have enough supports, or since these beams are not attached to the rest of the mesh, this expression, F equals Kx, does not have a solution. If you try and find the inverse of the stiffness matrix, say you want to do this in MATLAB, you want to find the inverse, you're going to get a message. It does not exist, there's no solution, there's an error. So that's what this message means. There aren't enough supports, or your mesh is not connected. So now that we know that the beam elements are not connected, and here let me cycle to a different mode shape and click apply. Let me slow this down, and again it's the beams. The beams are not connected. This is the benefit in using a normal modes analysis. This will tell you if there is a disconnected part of the mesh. It will also tell you if your mesh is properly supported. So that's why I'm recommending that you perform a normal modes analysis. First, make sure everything is connected to each other properly. Then after that's okay, then perform a statics analysis. So here, let's go ahead and fix this. Let's go to the meshing tab. And if you look at the FM actions group, there's this button here with a lot of points. It's called equivalence. Click that button. Here, click apply. And let me do this again. Let me undo this. Let me clean everything up. And let me click apply again. Here, if you look at these purple circles, these are the nodes that have been merged into each other. If you remember back, for the nodes of the beams, we have two nodes on top of each other. Let me go ahead and undo this, and let me turn on the labels again. So this is before equivalence. Look, I cannot read the label, and then this is after equivalence. Now I can read the node ID. It's 1819 here and 1827 here. So those two duplicate nodes have been combined into each other. Let me go to analysis, click entire model, and let me select the test run and click apply. Click yes on all these dialogues. And remember, always make sure that the F06 file has no user fatal messages. So here, this is the model test run F06 file. And you can see that there are no user fatal messages in this file. This is good. So let's go back to Patran, select HDF5 and click apply. Let me turn off the node IDs. Let me go to results, click on deformation, click the first mode, and click apply. So this is the first mode shape, if you will. Let's go ahead and animate it. Okay, perfect. Let me turn off the original, or actually I'll leave it on. Let me go ahead and change the color a little. Let me animate this again. So look at this. my wing box structure, if you will, it's now fully connected. If you look at the beams, and let me undo this. Let me hide. Here I'm going to select on tab 1, tab 2, and tab 3. Let me deselect the checkbox for show and deform and click apply again. And let me slow this down. And here you can see that in yellow, that's the geometry. That's the geometric curve. What you can do here in the home tab under the miscellaneous group, click on the green button. The green button is going to hide all the geometry. So now the yellow curves are hidden. And now what do I have? Here is the mode shape of my wing box. Here you can see that the beams are moving along in the eigenvectors. So this is good. This is telling me that this structure is connected properly. Here, let's just go ahead and take a quick look at the second mode shape. And let's go ahead and take a look at the animation. So this is moving horizontally, if you will. And here again, the mesh seems to be connected properly. Okay, perfect. So we're done with the normal modes analysis. Our beams are properly connected to the rest of the mesh. Now let's go ahead and go to entire model. Let's go ahead and select the model statics job name. This is the old job that we had before. And before I do this, let's go to the loads tab. Let's click on load or create load case. So we'll call this first one load case 1. And for the input data, we're going to select the supports and then the first force. Click OK and apply. Then we're going to create a second load case 2. Here's the name. Click input data. We're going to select these supports. We're going to select the second force. Click OK and click apply. Now we have 2 load cases. Go to the analysis section, click entire model, click model statics. So here it's selected to linear static. Now what about the subcases? Delete and remove the old default load case. Select load case 1 on this box, select load case 2. These are the load cases that are going to be considered for the statics analysis. Click OK, click apply. Now we're performing the statics analysis. And remember, always make sure that the F06 valve does not have any user fatal messages. So let's go ahead and type in user fatal message. Click find all, and you can see there's nothing. Here, let me delete the old searches. Find next, find next. It cannot find the error message. Good. Now, if we look through this file, we actually get some results. We get some results for the stresses, I believe. Okay then. So this has been a success so far. Let me import the results. Let me go ahead and look at the deflections. So here, let's go ahead. I got too much data. Go to the analysis tab, click on delete for the H5. Delete the old H5 for the model test run. If you remember, that file was for the normal modes. And if I go back to the results, I have data for one load case and second load case. Let's look at load case 1, and we're only interested in the displacements. So let's go ahead and select displacements for the color plot and the shape plot. Perfect. So here you can see there's some twisting because of the point load. And then let's look at the second load case. I've selected row 2 here. And here, since the load is going upward, we get a twisting as shown here. Okay, perfect. So this is what we've done so far. Let me delete some of these objects. Let me close these text files here on the right. So far, we've used Apex to build the geometry in the mesh. My recommendation is that you use another tool to build the geometry. So Patran does really well when it comes to supports, loads, and meshing and things like that. But you can also build geometry in Patran, but it's just going to take a long time. My recommendation to all FEA user is to use MSC Apex for cleaning up your geometry, modifying the geometry, and building your mesh. Or alternatively, you can build your geometry in CAD and then use Apex to mesh your geometry. But here, since I'm talking to a lot of Patran users, here I've shown you how to use Apex to build geometry and create the mesh. We've selected some units, so we're using meters kilograms for the mass, and then Newton for the force. After we've defined what our units are, we import the mesh to Patran. We've gone ahead and defined our supports and our loads for 2 load cases. We added some beams that represent the stringers, if you will. And now what about composites? I am not going to show you how to create materials for composites here. What I'm going to do, I'm going to take this existing bulk data file. This bulk data file has materials. It has materials for, here, let me go ahead and modify this a little. Let's go ahead and see if I can modify this a little. The comments are a little too bright, and I want to make this a little lighter. Okay, perfect. So here you can see that I have a mechanical properties for a glass epoxy unidirectional tape. I have some mechanical properties for core layer. So here I've defined E1, E2, and things like that. Here in the P comp entry, I define multiple layers. I have a layer for the 90, 45, negative 45, 0, and so on and so on. I'm using the symmetry option. So here these layers are going to be mirrored. Here, this layer is a core layer. So let me do this. Let me just import this bulk data file that contains the materials and the P comp entries. So that would be here. Click OK. If you look here on the properties here on the left side, you have a new P comp layer. This is the P comp layer that we had a moment ago. And then I think it might make sense to open the composite layer. So here, let's go ahead and show the properties. So here are layers 1 through 9. And remember, we're using the symmetry option. So this is actually an 18 layer laminate, if you will. Let me do this. Let me go ahead and modify this. No, I'm going to leave that as is. Let me go ahead and right click this and modify the application region. So here I'm going to select all the 2D elements. Let me go ahead and here I've clicked the broomstick icon here. So this go ahead and removes everything that's been plotted. And remember, when you select objects, you can either select geometric options. So here if I try and select a geometric option, there are none. There are no surfaces to select. There are no geometric surfaces to select. So what I'm going to do is click on this button, shell element. Now if I select objects, I can select all the 2D elements. So let's go ahead and click add, click OK, and click apply. And here it's giving me an error saying that I haven't specified information here. Let's go ahead and open this tool once, click OK, and click apply. Click yes for all. Here, before it was using the dummy material and the dummy thickness, but here I'm saying, hey, ignore everything I've defined for the 2D elements, use the composite. So now here in the bottom left, it's told me you've modified pcomp.1. Now let's go ahead and do this. Let's go ahead and try and perform the analysis. So let's go ahead and do that now. Click apply, say yes, yes for all. Click desktop. Let's go ahead and open that statics file. Here, let's go ahead and look for that pcomp entry. Okay, perfect. I now have the pcomp entry in here. Let's go ahead and import the results. And one thing I forgot to do, always make sure there are no user fatal messages here. Okay, perfect. There are none. Let's go ahead and import the results. Let's look at the deflections real quick. Click apply. Okay, perfect. So this is what the translations look like for this example. And here the translations look really odd for this. Let me go ahead and look at the other translations. Okay, I think this makes sense. One thing we need to look at, what do the layers look like? Here, I'm going to be using a different tool called the Viewer Web App. One good thing about the Viewer Web App is that it lets you look at your beam cross-section and the layers of your composites. So let's go ahead and import that bulk data file. And let's go ahead and turn on all the layers. So now if we zoom in very carefully, and that's what I'm doing right now. These are what my layers, what my plies and my core look like for the pcomp entry. Now, there's one thing I don't like here. The color. The color doesn't tell me what the angle is. So here I can click on this button and this will change the colors. Red is a 90-degree layer, blue is a positive 45-degree layer, green is a negative 45-degree layer, and gold is a 0-degree layer. So now, what do I do now? I don't like these top outermost 4 layers. So what do we do here? Let me go and modify that layup. So here under model materials pcomp1, let's go ahead and modify this. Let's go ahead and delete these 4 layers. So here I've selected these 4 layers that have a thickness of 1.25 millimeters. So let's go ahead and delete those layers. Great. Now I have these 4 layers and then the core layer. Let me minimize this and let's go ahead and click apply. And let's go ahead and right click and show properties again. I want to make sure there are 4 layers and then the core layer. Now let's go ahead and do this. Click entire model. This time I'm just going to output the analysis file, the bulk data file. This says write only the bulk data file, skip running MSC Nastran. And now what I'll do is I'll open the viewer again and I'll go ahead and select that bulk data file, the statics bulk data file. And let's go ahead and zoom in very carefully. And let's go ahead and look at the thicknesses. And let me change the color. Okay, perfect. So now I have, how do I say, 4 layers at the top and bottom, and then I have my core layer in the middle. And then here, one thing we can do also, we can inspect the beams. So let's go ahead and turn on the beams. You can see there's one problem with the beams. They intersect the thickness of the laminate. So we have to define what's called a offset. Now the question is, how much of an offset do we need? Now here, let me see if I can know what the thickness of my laminate is. So here, okay, perfect. So it's 0.011. So this is what I have to do. In Patran, let's go ahead and define an offset for the beam element. So here under properties 1D, right click on that and click modify data. Here you get these 2 offset boxes. Let's go ahead and say that the offset is 0.011, I believe was the offset. And let's do this for only one node of the beam elements. Click OK and click apply. Go to display, load BC element properties, select the option 3D full span, click apply. So you can see that now one end of the beams have been offset. Now, the offset wasn't enough. We have to include the total thickness of the laminate and half the height of the beam. And half the height of the beam, if I remember, the beam has a height of 0.1. So half of that is 0.05. So this is the offset due to the beam. And then 0.011, which is the thickness, total thickness of the laminate. So let's go ahead and total thickness of the laminate. So again, the total thickness of the laminate, that's reported here. If you right click on pcomp1, show properties, here in the bottom left hand corner, it tells you total thickness and stacking sequence, 0.011 meters. Okay then, so let's go back to the 1D property, right click that, modify data. Let's go ahead and do some math here. So what's our total offset? 0.061, that's the total offset. So let's go ahead and type in 0.061. 0.061, click OK and click apply. And now let's look at our offset here, and let me make sure I did this right. Right, and here, let me make sure I'm doing this all right. I think my math is off. So here, let me make sure I'm doing this right. I'm getting my numbers confused. I'm getting my units confused in this exercise. And again, I didn't rehearse this, so that's why I'm a little rusty today. So this is 0.01 and 0.5. I did the math and it's still not right. So let's do this. Let me glance over this. And let me just do this via trial and error. So here, 0.111 maybe, click OK and click apply. And then I think what I have to do is turn this off and on. So this is before the offset and this is after. Okay, let me go back to this and modify this. Okay, this is not cooperating with me today. Let me do this. Let me use an offset of 2. Click apply. And now let me display this off and on. I think what's going on here something is going on here. Let's look at the element properties. Click OK. Oh, I was modifying the wrong input. Okay. I was modifying the bar orientation vector instead of the offset vector. So let's supply the value here. I think it's 0.061. Click OK, then click apply. Okay, this looks a little better. But one problem that's happening, it's actually moving the cross-section upward. What I need to do now is use a negative offset here. So we're moving this in the negative Z direction. Let me go ahead and make sure I'm turning everything on full span. And now it's no longer working. Let me look at the modified data option again. Let me use commas. Maybe that's messing things up. Negative 0.061. Click OK and click apply. Let's go ahead and turn this off and on. Oh, now it doesn't want to work. Let me go ahead and do this for the other option too. So offset at node 1, offset at node 2, click OK and click apply. Okay, this is what I'm going to do. I'm going to skip that part and I'm just going to output the bulk data file. So here for method, only select analysis deck and click apply. Click yes. And now what I'm going to do is, okay, now we're getting a different error. Let's go ahead and modify this. Okay, so let's go ahead and redo this. You have to be careful with the forms here sometimes. Type in negatives 0.061 meters. Click OK. Click select application region. Let's go ahead and reselect all of these elements. Click add, OK, and apply. This is one thing sometimes when you're working with the tool. You fill out all these input boxes and at the end it doesn't do what you want, so you have to repeat the process. So here, this is the offset for one of the ends of the beams. And now let's go ahead and do this for the other end. So we'll go ahead and select this beam properties, select the second offset, type in the same offset, click OK. Let's go ahead and make sure there are elements in the application region. Okay, we have some beam elements here. Let's click OK and click apply. And then if we look at our beam elements now, you can see that there is an offset. So let me go ahead and reorient this a little. So now you can see that there's an actual offset for the beams. So here in this region is the laminate. Here's the end of the laminate, and this is where the rest of the cross section starts. So let me go to analysis, entire model, analysis deck, and click apply. Click yes, yes, and yes. I have a new bulk data file. Let me close this other window. Let me open this new window here. Let's go ahead and go to File, Upload, and select that statics file and click Upload. What I want to show you now are the beam elements. So here, if we look at the beam elements, let me go ahead and shift through some of these other options. And let me rotate this a little. Okay, perfect. Let me zoom in and let me turn on the laminate. Oh, even then, this is still not enough. Here, my offset was still too much. I didn't do the math right, but generally it's going to be, actually, I think it's half the thickness plus half the height. So let me look at this real quick. So I think it should be 5.5 maybe. That's okay. I'll leave it up to you to determine the proper offset for this beam. You can use the viewer web app to go ahead and take a look at what your offsets look like. You can turn on all the plies and look at that. Actually, let me do this. Let me pause the video for a quick moment. Okay, so I took a look at what the better offset value is. So let me take a few moments to describe how to get the correct offset. Back in Patran, go to Tools, go to Beam Library, and turn on Calculate/Display. This is going to tell you the distance from the bottom fiber. Let me look at this. Right. This is going to tell you the distance from the bottom fiber to the top fiber. If you look here at all this data, you get this information here. Centroid relative to origin. You can see that if you go on the vertical, if you go from the vertical x-axis, if you will, to the centroid, that's approximately 0.058 meters. So let's go ahead and copy that. So we want to do, let's see, if we go back to the viewer, we want to know the distance from this edge, which are the 2D elements. We want to know what that distance is. So we want to know what this distance to this distance here is. So let's go ahead and calculate this a little. So we know this distance here to this bottom line, if you will, it's 0.058 meters. But what about this distance here from the top to the centroid? That's going to be 1 or 0.1 minus that distance. And then we have to add onto it half the thickness of the composite, 0.011 divided by 2. And then here I'm going to round this up to 0.047, or we could use 0.0471, or actually let me do that. Let me go ahead and do this, 0.0472. Right click on this. Here, let's go ahead and use that. Negative 0.0472. Go ahead and do that for both ends of the beams. Click OK. Let me close that window. Click Apply. Let's go to the entire model. Let's go ahead and make sure we select Analysis Deck. Click Apply. Click Yes. And let's go ahead and redo this. Let's go ahead and import that new bulk data file. And sorry for taking a long time with the offset. Like I said, I didn't rehearse this. A lot of things that I've done in this exercise have been done on the fly. The spar as an example. I didn't plan for that. I added the spar, the stringers, these beams. I didn't plan for that. That's something I added during this video. So again, apologies if the video was a little coarse. So let's go ahead and do this. Let's go ahead and look at the model. Let's rotate it a little. And let's zoom in very closely to where my beams are. And let's turn on all the detail. And let's zoom out a little. Okay, this looks a little better now. Okay, so here the dotted line, this represents the beam offset. Here, these layers, this is my composite laminate. And then here in pink, this would happen to be my beam cross section. Now let me go ahead and zoom out a little. Let me turn on the beam cross section. And here again, the dotted lines represent the offset. So that's how you define your beam and the offset. Pay very close attention to the beam offset. Here, as you saw in this video, it's something that can actually get really complicated. So definitely take your time when defining that. Now, there's one thing we need to do in Patran. We need to talk about the 0 degree direction for our plies. We don't know what the 0 direction is for the plies, so we have to discuss that real quick. The 0 degree direction for the plies is as follows. Go to properties, go to modify, or actually show, and here you can display what's called the material orientation and click apply. Okay, let's go ahead and see material orientation. This is not working now. That's okay. There is an alternative method of doing this. Go to display plot material orientation. This should work. So let's go ahead and select a few elements here. Okay, perfect. So this is telling you the 0 degree direction for these elements. And then let's go ahead and do this. Let's go ahead and turn on the Y direction. So this is telling me the 2 direction, or it's not telling me the 2. This is telling me the 0 degree direction for the composite. So let me deselect this again. You might be asking, how do I control the 0 degree direction? And this is how you control it. In the pcomp entry, I believe, let's go ahead and modify this. You get this option, material orientation. So this is what I'm going to do. I'm going to create a new pcomp entry that's called pcomp2, and this is for the ribs. Let's look at the input. So here, let's go ahead and select that pcomp entry, pcomp1, and let me make sure I'm doing this right. Okay, so it's a little confusing here. So let's go ahead and create 2D. Let's see, what am I going to do here? Create 2D shell, pcomp1. Here, let's rename this a pcomp2, ribs. Input properties, let's go ahead and give this a pcomp1 for the material orientation. There are a few ways you can define the 0 degree direction. You can either use a coordinate system where the x direction of that coordinate system is the 0 degree direction for the most part. And actually, let me do that. Let me go to geometry and click on coordinate system, 3-point. And let me try to do something a little different here. Let me define the following. So let me move this here, -1, and do that. Let's go ahead and see what that looks like. Okay, perfect. Yeah, let's do this. And let's maybe do another coordinate system. We'll define it at 2. And let me use the Euler method. So here, let me go ahead and move this to maybe -2. Let me rotate this about the Z, maybe 45 degrees. So about the Z, 45 degrees, click OK and apply. Okay, perfect. So now let's create some properties here. So here, create 2D shell, pcomp2 for the ribs. Go to input properties. Let's select pcomp1, which is that one laminate. The material orientation. Let's select this coordinate system. So what's going to happen now, it's going to take the x-axis of this coordinate system and it's going to project it onto the elements for the ribs. So it's going to do the projection. So then the 0 degree direction, if you look at this coordinate system, you can see the x-axis is in this direction. So when it performs the projection onto the 2D elements, the x direction or the 0 degree direction is going to be in this direction for the ribs. So that's what we've done here. Let's go ahead and look at this. Okay, the pcomp1, material orientation. Let's go ahead and select these elements in the middle. So let's go ahead and see what's the best way of doing this. Okay, perfect. So let's just go ahead and select these elements, click add, click apply. Yes, for all. Let me make sure I'm using the bonding shear here that's given. Let's go ahead and click right click, modify data. For the bonding shear, I'm going to use this value and click apply. And here, can I just modify the name here? Click apply. Okay, perfect. So there we go. So we've created this P comp for the ribs. And now if we look at the direction of the 0 degree direction, let's go ahead and select this element. Perfect. Look at that. So you can see that my 0 degree direction is now running in the Y direction, if you will. And that's because we're using the x-axis of this coordinate system to orient the 0 degree direction of this laminate. Now, let me use a different option for the orientation. So here, let's go ahead and do this. I'm going to offset the 0 degree direction by maybe 45 degrees. So let's go ahead and click OK and click apply. Let's go to this tool and reset all the arrows. And here you can see that the direction of the 0 degree direction is now in this direction. It's been offset by 45 degrees. Alternatively, if I want to use this coordinate system 1, I can right click on that, select CID, select this coordinate system 1, click OK and click apply. And if I go back to that tool, click reset, and now click these elements, you can see what the direction is for the 0 degree direction. And now you might be asking yourself, okay, in which direction are the plies being stacked? So you can use the viewer web app to help understand the direction. So let me do this. Let me turn on layer 1. This is layer 2. And let me zoom in very closely because since the plies are so small, I have to look in very closely. So let's go ahead and zoom in. Let me move this up a little. Let me keep zooming in. Let me translate this down a little. So this first layer, this was layer 1. This is layer 2. This is layer 3. Layer 4, layer 5. So you can use the viewer web app to look at the layers 1 through 10 in this case. Now here, if you look in Patran, this is how you can determine the stack and sequence order. Turn on the Y direction checkbox and click apply. And let's go ahead and select the wireframe and click these. If you use the cross product of the X and the green axes, this is going to tell you the Z axis, if you will. The Z axis is the direction of your stacking sequence. Here, if you do the cross product, there's a blue arrow, if you will, that goes in this direction. So layer 1 would be here on the top, and then layer 2, 3, 4, 5, and 6. Let me actually do this. Let me do this for the top. Let me do this for the top here. So let me turn that on. So here, let me go ahead and turn this off. So this is layer 1. If you look here in Patran, if you look at this element, do the cross product. Do the cross product of the red and the green axes. This gives me a third axis, and it goes in this direction. So what does this tell me? Layer 1 is here, layer 2, layer 3, layer 4, layer 5, layer 6, 7, 8, all the way through 10. That's going to align with what we see here in the viewer web app. So again, determine the 0 degree direction, determine this y-axis, do the cross product. That tells you the stacking sequence of your layers, if you will. Okay then, so let's see, what is there left to do? I think that may have been the last thing. Let's go ahead and do one last analysis. Click entire model. Let's go ahead and do model test run. Oh no, statics. Click apply. Now we're going to perform that full statics analysis. Let me go ahead and stop this here. There's a problem. So let's go ahead and see if we can diagnose the problem. So this beam has information. Let's go ahead and look at the second laminate. This property does have elements. Let's look at the next property. There are no elements here, so that's a problem for us. So let me do this. Let me go ahead and select these inner elements, which are for the ribs. Click OK and click Apply. And then here, I get this old error. I don't expect this error to happen. But here, that error is telling me this. Hey, you forgot to click on Modify Properties. You forgot to add data. Here, I'm just opening it once and clicking Apply. And then that error should not happen. So let me do this. Let me open these one by one. Let me make sure there's data here. It's very easy to click so much and some of the data is left out. So here I'm making sure that there are properties, and here, lo and behold, it didn't add the elements. So let me do this again. Click OK, click Apply. And then here, let me open this dialog again, click OK, then click Apply. Now, again, let me go ahead and look at the elements. Okay, that looks good. What about here? Okay, that looks good. Click here. Okay, that looks good. Click Analysis, Entire Model. Now click Apply. Now we can perform the statics analysis with 2 load cases. And so let's go ahead and look at the, how do I say, the F06 file. And this one's taking a little longer. I think since I have so many things open up in this viewer or in this virtual machine, it's slowing down my machine. So let's go ahead and close some of these objects. And let's go ahead and open the F06 file. And remember, always look for any user fatal messages. You never want this message. There are no messages like that. Let's go ahead and import the HDFI file. Let's look at maybe some results here. Let's look at a quick displacement results. So this is what the displacement looks like. It looks a little odd. I believe the reason why the displacement looks off is because in this region, there's nothing to stiffen this region. So that's why that's happening. And now let's go ahead and take a look at the failure indices. A quick comment about the failure indices. You might be, how do I say? You might want to look at your failure indices, but you need a few things for that. So let me go ahead and show you what I mean by this. So what you want to do is look at the quick reference guide for MSC Nastran and then look for the pcomp entry. If you want to display failure indices, apply stresses and strains, you have to fulfill a few conditions for that. So if I look here, if you go to the pcomp entry and look at remark 7, it says in order to get failure indices, this is what you have to do. You have to make sure that the stress case control command is present. So if you look in that bulk data file, if you go to the top, the stress command is present in the case control section. So that first requirement has been fulfilled. SBFT SOUTI on the pcomp entry must be defined. So what is SB? SB is the shear bonding and FT is the failure theory. So SB is in field 5 and failure theory is in field 6. So let's go ahead and look at pcomp. So let's go ahead and look for it. Okay, so here, right now we're using the large field format. This is designated with the asterisk. Maybe we don't want to use that format. So what you can do is go to Analysis, Entire Model, click on Translation Parameters here on the right. For the card format, select small, click OK. And here, let's just go ahead and select full run. Click yes, yes again. And now let's look at the new bulk data file. And now we're using the small field format. Note that there are no longer asterisks. When there's an asterisk, that's the large field format. So let's count. This is field 1. It's 8 characters long. This is field 2. It's 8 characters long. Field 3, 4. This is field 5. So I do have a shear bond value here. I need FT. So if we go back here to the second requirement, I need SB, which is in field 5, I believe. 1, 2, 3, 4, 5. Field 6 is the failure theory. Field 6 is the Hill failure theory. So there is an FT. Now, SOUTI, I believe that's the output for the layer. So stress or strain output requests, and you will see that they're all yes. SOUTI, it's yes and yes. Okay, perfect. Now let's keep looking here. What else do I need? I need XT, XC, YT, YZ on the mat 8 entry. So let's look for mat 8. So here's my mat 8. And let's go and do this. Can I open another copy of this? That's okay. Or maybe, yeah, let me do this. Let me open this in Google Chrome. And what I want to do is show you the mat 8 entry. That's where you specify what your failure criteria is for the 1 and 2 directions. So that's why I want to open it. So let's look for mat 8. And we'll go ahead and jump to that value. So if you look here, fields 15, 16, 17, 18, and 19. This is field 1, field 2, all the way to field 10. Then on the second row, field 11, 12, 13, 15, 16. So these values, they specify what the limits are for your layer or your material. So we need to confirm that's here. So if we look here, field 11, 12, 13, 14, field 15, 16, 17, 18, and so on and so on. These are going to be my fields for XT, XC, YT, YC, and S. So let's go ahead and make sure that's here. Okay, everything that I need is there. Let's see what else. And I think that's it. Right. So as long as you satisfy A, B, and C, you will get the failure indices output to your H5 file. Now let's go ahead and do this. Let's go to the viewer. And let me do this. Let's just go ahead and look at the results here in the viewer. Now, one of the reasons I like to use the viewer, one, it's free. Number two, you can look at the direction of your failure indices or your apply stresses. So let's go ahead and import the H5 file, which I forgot to do here. So let's go ahead and select the H5 file. Click upload. And now here, let's go ahead and look at the stresses. Select the load case, and here let's go ahead and select layer 1. So these are the apply stresses in the one direction for layer 1. Let's turn off the shape plot, and now there's an option here to display the direction. So here, it's telling me what the direction is for my layers, and you can see there's something off about this. These elements have a really odd direction, which I have to look at in a moment. Let's see if we can fix that later on. But here, these again are the apply stresses along the one direction for layer 1. This is layer 2, layer 3, 5, 6, so on and so on. If we want to, we can look at the failure indices, but I won't look at that for right now. What I want to look at now, let me double check that. So let's go ahead and look in Patran. Let's make sure that these elements on the side are in the right direction, and they're not. So let's see if we can look at what's going on here. So this is not going as I plan. I'm trying to diagnose, okay, I know what's going on. So these elements here, they're using the x-axis of coordinate system 1 to orient the 0 degree direction. So if you look at this red axis, you can see that it's parallel to this axis. So maybe this is not something we want. How do we fix this? If we go back to that property for the 2D pcomp1, let's go ahead and modify that. Let's use coordinate system 0. and click OK, then click apply. Now, let's go ahead and make sure that there are properties and that there are elements selected. Okay, perfect. Let's go back to that tool. Let me reset this. And now let's look at the direction. Perfect. So you can see that now the x-axis is pointing in the direction that I want. So these are all in the x direction of the bottom left-hand coordinate system. This bottom left-hand coordinate system is the default. This is the basic coordinate system that you always start off with in Patran and MSC Nastran. So you can see that the 0-degree direction of the laminate is now parallel to the x-axis of the basic coordinate system. So that's what I wanted. So now if I go ahead and click entire model and reanalyze this, I should get results. So let's go ahead and click yes. And as always, let's go ahead and make sure that there are no user fatal messages in that F06 file. So let's go ahead and give this a few moments to finish. And you know what? To improve the speed of this, let me close Apex. If I open the task manager, I have a feeling that I have a lot of consumption of my resources. So let me close some other tools here. Okay, that analysis is complete. So let's go ahead and make sure there are no user fatal messages. Perfect. Things look good here. So if I wanted to, I could import the results here in Patran. You could also look at the apply stresses here. So here, let's go ahead and look at the apply stresses for layer 1. And here, let's go ahead and look at maybe 1. Yeah, it gets a little complicated when you're looking at layer stresses here. So that's why I prefer to use the viewer web app if you want to look at that. Another benefit in using the viewer is the following. Let's suppose we want to look at beam results. So how do we do that? Let's go here. Let's turn off the 2D elements and let's only display our beam elements. So if we do this, this is what our beam elements look like. Say you want to look at the bending moments in this element. Let's go ahead and open the post-processor panel. Let's go ahead and get results for beam forces. And here I don't have any beam forces. I only have beam stresses. So let's just go ahead and take a look at the beam stresses for now. Here I've selected load case 1. Let's go ahead and find these bending stresses. And let's zoom in real closely. Let's turn on the arrow plot. So here, these arrows are pointing away from the cross section. So these are in tension. Let me go ahead and turn on the stresses for the other end of the beam. So let's go ahead and select these 4 rows. So you can see that the arrows for this element are pointing away from each other. So it's in tension. And then here for the bottom, the arrows are pointing towards each other. So this is in compression. Now you might be asking, okay, how do I get the beam forces for this? What you could do is the following. Go to analysis, go to entire model, go to subcases here on the bottom right. Here, let's go ahead and create some load cases. Select load case 1 here, click output requests. Here in this list, look for something that says element forces or forces. Here, element forces, click OK and click apply. Click yes to confirm the edit. Do this again for load case 2. Go to output requests, find element forces, click OK and click apply and click yes. So here I've turned on the output of the element forces. So now let me go ahead and redo this analysis. If you look in the bulk data file, you notice that there's a new command here, force. Output the element forces, stress. Output the element stresses. Now what I can do here, let me redo this all over again. Let me import the bulk data file that has been created again. And let me import the H5 file that contains the result of this Nastran analysis. And now let's go ahead and take a look at the element forces, and let's go ahead and make sure the beam elements are on. Let's go ahead and display that. Change the background. Let's go ahead and click on post processor. Let's look at the results for load case 1. Here I'm looking at the element forces. Let me zoom in very carefully. And right now we only have points to indicate the scale or the magnitude of the element forces. What I can do is click on arrow plot, and this shows me that this value is a moment about this axis of the cross section. Let me turn on the second option. Now I have a moment for the other axes, and here we only have values for this, for this end of the beam. Select the other values, and now I have the moments for the other side of the beam. Here, let's go ahead and do this. And now I have all the element forces for all the beams. Now there's an additional option here that is worth mentioning. So here, let me do this. Let me turn on everything. Let me turn on all the 2D elements. Let me zoom out a little. You might want to navigate into the interior of your wing. How do you do that? There's an option here called first person. Click enter controls. Now you're in this special mode where you can navigate the model like a video game. So here we're moving into the interior of the wing. Let me rotate the camera. Now I'm in between ribs 1 and 2. So here, let me zoom out a little. And right now, again, I'm inside the wing. You can see the skin for the top and bottom. And let me do this. Let me rotate this a little. And now let me go into the post-processor mode again. And now let me go into navigation again, enter controls. And now I can move the camera like I'm inside the wing. Here you can see the ribs, the skin. Let me zoom in here a little bit more. I can look at additional data. Press the escape key to exit the controls, and then you can decide what exactly you want to look at. Maybe just moment 1, maybe the shear forces, and so on and so on. If you want to return to the original view, you can click on first person, and now you're back to the standard way of looking at your model. So that's first person mode. And there's one thing that stood out to me. Okay. Yeah, the green had me a little confused. Let me go inside again. So when I was looking at this, right. So this green section that I'm looking at right now, this is the section for the spar. This green is for the ribs. This yellow is for, well, I guess it's another spar. The top and bottom is the skin, if you will. So, okay then. So what's there left to do? So that is the next section in this long tutorial. We defined some composites. We defined some beams. We performed a statics analysis. Again, a lot of this was not rehearsed. I'm just making this up as we're going. We looked at the results in the post-processor web app. Here in this case, we looked at the layer stresses for the composite. We looked at some beam stresses and beam forces. Now, the last thing I want to leave you off with is, how do you set up an optimization? My recommendation is to use the newest and latest interface available for Nastran SOL 200. There are a lot of reasons why it's better to use the web app to set up your optimization, but I'm just going to show you how to set up the optimization. Now, what I'm going to do is I'm going to copy this bulk data file. I'm going to put it in this directory, starting files. And I'm going to make a modification here. Here, let me modify this pcomp entry. So this is layer 1, layer 2, layer 3, 4. And then here we have a core layer. Since we're using the symmetry option, we only have to define half of the laminate. Suppose we delete the symmetry option here on the far right. This is what we have to do. We have to create another layer here, here, and here, because now we're responsible for every laminate option here, or we're responsible for defining every laminate. But here we don't have to do this because we're using the symmetry option. Now here, this is what I want to do. I want to beef up the layers. I want to make them 0.01 meters thick. Now I'll explain why I'm doing this in a moment. Let's go ahead and now configure our optimization. So to do this, I'm going to perform a very simple optimization. Before I start an optimization, I define what's called the optimization problem statement. So here you want to do two things. What are your variables? Thickness of layers 1, 2, 3, and 4. Those are my variables. What's the objective? Minimize the mass. What are constraints? No constraints. I want to keep this simple. So now let's go ahead and do this. Let's go back to the home tab. Here, let's open up the optimization web app. Let's go ahead and open that bulk data file. Click upload. Let's go ahead and search for the thickness of each layer. Let's go ahead and look at this real quick. Oh, there's something a little off here. Oh, there's a second pcomp. So there are two pcomps in this file. Let me go ahead and make sure the other pcomp is here. So let's go ahead and search this. So we do have a pcomp 1 and 2. Right, so pcomp 1 is for the top and bottom skin, and then pcomp 2 is for the ribs and the spar. I think here I'm just going to focus on pcomp 1, which is for the skin. So here, let's go ahead and define and set these layers as design variables. And here, the smallest thickness possible is 1.25 millimeters or 0.125 millimeters, or actually, right, the smallest thickness possible is the thickness of one ply, which is 0.125 millimeters or 0.000125 meters. So let's go ahead and do that. Here, if I wanted to say, hey, at most use 10 layers, what I would need to do is this, 0.00125 times, or actually, let me do this. Let me delete this right now. We want to do this optimization in ply numbers. Right now, I was doing this optimization in thickness. So if you use ply thickness variables, this is in units of length, like meters, millimeters, inches, and so on and so on. But some of you might want to use ply numbers instead. In this case, you want to use integers. So what do we do here? You can define what's called another design variable. So 1, 2, 3, 4, 5. I want to say start at maybe 10 plies or 10 layers. And then the smallest value is maybe 11 layers. So let's go ahead and type in 11 here and here. Here, I want to say use only integers between 1 and 11 and go in increments of 1. Here, what happens is sometimes, say at the end of the optimization, it tells you you have 3.1 plies. 3.1, that's a fraction. I don't want that. I want either 3 or 4. So what I do is I define a DD val entry that says 1 through 11 in increments of 1.0. So that's what I'm defining here with this box. If you look here on the right, there's a DD val entry here in the bottom right, 1 through 11 by increments of 1. So use only integers for this entry. Here I'm saying start off with 10 layers, range between 1 or 11 layers. Now I have to define a D-link. Here I'm going to say that x1 is going to depend on variable y1. But y1 is an integer value. It's the number of layers. Here I'm going to specify that the thickness of one layer is 0.000125 meters. And let me do this again. So x1, x2, x3, and x4, that's the actual thickness of the layer. It has units of meters in this case. Here, I'm saying that x1, x2, and x3, 4, they're equal to y1, y2, y3, y4 times the thickness of one layer. Okay, that looks good. Now let's go to the objective, minimize the weight, and download the bulk data files. And that's it. That's our optimization. So let's go ahead and extract the contents of the zip file. Let's go ahead and quickly run our optimization. Let's run MSC Nastran. Okay, perfect. So now remember that, or actually here, let's look at the variables. Here we see that we started off with 10 layers for all those different layers, but at the end we have 4 layers. Now, if we look in this directory, workspace B, if we look at the pcomp entry, and keep searching here, you can see that the pcomp entry has been automatically updated for me. So let's go ahead and look at this. So if we look at the old pcomp entry, the old pcomp entry had a thickness of 0.001 meters, but now we have 0.0005 meters. So if you do the math, let's go ahead and do some math. 0.005, let me make sure I have the units right here. Divided by 0.00125, that should be 4. Perfect, it's 4. So here we started off with 10 layers, and then we ended off with 4 layers. Since this was just an objective minimization problem, it moved all, or actually, this should have actually been 1. Okay. Let me make sure I've done this properly. There's always a detail here. This should have actually gone to 1, but it's converged a lot sooner, which is really interesting. Let's see if we can identify why this is happening. Okay, 1 times 0.00125. Okay. Let me do this. Let me go to settings and turn on global optimization and click download. And I know this tutorial is becoming a lot longer than I was expecting, but let me continue on. Click okay here. Now what's going to happen now, the optimizer is going to perform multiple optimizations at different starting points, if you will. Here I was expecting a final solution of 1 layer for all these layers. We're either deciding a number between 1 and 11 layers. So that's why here we ended off with 4. That seems kind of odd. Sometimes what happens is due to tolerances, the optimizer will actually miss 1 local minimum and we'll find a different local minimum. So it's here. Let's go ahead and see if we can figure this out. Now, maybe it's not that. Maybe it's something else that I misconfigured here. And let me keep looking. Maybe something here stands out that I didn't notice. So we started off with 10 and then we minimized this. We're going from 1 through 11 in increments of 1. Yeah, this all looks okay. Let me look at this right here. It's gone to 5. Yeah, let's just wait and see what happens at the end. Okay, we're done. Interesting. Okay, let's do this. Let's redo this. So instead of starting with 10 layers, let's start off with 3 layers. This should drive the variables to 1. And let me add some label comments here. Number of layers for 0 degrees. number of layers. What I'm doing right now is I'm adding some custom labels to the variable so I know what they are later on. So it's 90, 45. I got my bearings here wrong. So it's 90 positive, 45 degrees, negative, and then here we're going to say 0. So let me make sure this is right. 90, 45, negative 45. So 90, 45, negative 45, and 0. X1, X2, X3, Y1, Y2, Y3, Y4. Okay, let's redo this, but this time let's go ahead and select local optimization. So again, this is only a weight minimization problem. There are no constraints. So the optimizer should move the variables to just one layer. So it's really interesting here that it's not doing that. So let's go ahead and do this again. And let's see what the answer is after this. And here hasn't even moved. Oh, here we go. 3 and 1. Okay, so number 1, it's moved the variables to just one layer. Before we started off with 3 layers, now we're ending off with 1 layer. If we open the updated bulk data file, which is in workspace B, if we look at that pcomp entry, you find that the new thickness is now 1.25 meters. So let me go ahead and space this out a little. So here, if you look at this value carefully, it's this value, 0.000125 meters. Okay, now let's go ahead and look at the mass, because the mass was kind of interesting. So let me do this. Wow, does the mass make sense? Maybe there was an issue with the density. I think what's happening here is that the change in the objective is so small that it's causing the optimizer to terminate early. I think that's what's going on here. I have to modify the settings for this optimization to really go forward, but that's okay. I won't distract you too much. The point I was making here is the following. That's how you set up an optimization. I recommend using the web app to configure your optimization. You'll notice that a lot of tools are tools that have been developed over the last 20, 30, maybe 40 years. So when you try and configure an optimization with these other tools, it might take you a little too long. The benefit in using the web app is that you can quickly configure your optimization and get the results that you need, like I showed in this video. Okay then, so I think we're pretty much at the end of this exercise. I think what's worth noting, or one last thing that's worth showing you, are the results, the mechanical results. So let's go ahead and do this. So let me open the viewer and let me show you what the results were before. During the optimization, you had this H5 file that was created for you. So that here it is. This H5 file contains the results for the initial and the final design, or for the original model and the optimized model. So let me go ahead and upload that here. So that was in this directory. Click upload. And here we're looking at the displacements for load case 1, for 0, or for design cycle 0. Design cycle 0 is the initial design. If we select this other checkbox, these are the results for subcase 1 or load case 1 for design cycle 1, which is the final design. And if you look at the values, the deflections are different now. Here, let's go ahead and look at these deflections, and let's turn on the maximum label. Let's go ahead and see what the maximum and the minimum displacement was. So the maximum displacement is happening here in node 1917. It's about 3.5 millimeters. Let's look at the optimized deflection. I expect it to be higher, and I'll explain why it's higher in a moment. Before we were getting 3 millimeters, but now we're getting 9 millimeters as the deflection. You might be asking yourself, why is the deflection higher? The deflection is higher because we reduced the number of layers from 10 or 3 down to 1. We've made the structure lighter, so the results increase slightly, or the deflections increase slightly, rather. Okay then, so I'm pretty much at the end of this tutorial. Here, what I wanted to do was a lot. I know many of you might be students in an undergrad career or role, or rather some of you might be undergraduate students. This might be your first day trying to use Patran, trying to use MSC Nastran. It might be worse. You might be asked to do an optimization, and there you are, you're 20 years old being asked to do this hardcore level of engineering. I was in your seat. I was there doing the same things you were asked to do. What I wanted to do with this video is I wanted to show you how to do this. It doesn't have to take weeks or months of learning. It's actually quite simple once you're used to it. So let's go ahead and cover what we went through. Number 1, geometry. Do not use Patran to create geometry. Use MSC Apex or use some other CAD program to build your geometry. Use Apex to build your mesh. It will quickly help you build your mesh, as you saw earlier in the video. After this, you could use Apex to create your loads and boundary conditions and materials, but I know if you're watching this video, you've been asked to use specifically Patran. Use Patran to define your loads and boundary conditions. Here, I showed you how to define some beams. One thing I forgot to describe, the orientation vector for the beams. So here, if you go to the Fem label tool and you select display orientation vectors, these purple lines are the orientation vectors for your beams. Also, later on, you might be asked to look at what the degrees of freedom are. There's a button here that displays the degrees of freedom. And here, I believe, I don't know if I'll show you, but in this case, it doesn't show you. Right. So here, again, you can either display the degrees of freedom or you can display the orientation vectors. If you wanted to, you can use this to define and pick some beam elements, some 2D elements like the C quad 4 and the C bar elements. So going back here, we looked at the beams. We looked over how to create composite materials. There we're really interested in defining the 0 degree direction. We were also interested in determining the stacking sequence for your layers. A lot of the time, you never look at the thickness of your layers. So here, let me show you what the thickness of the layers look like here. Let's go ahead and turn on everything. And right, so this is what the layers look like for this case. Here we have 90 degree, 45, negative 45, and the 0 degree layers, and then the core layer. So after this, we looked at how to configure statics analysis. We went through how to define 2 load cases. We went over the most common user fatal message, which is user fatal message 9050. So this means that not enough supports or unattached mesh. If you remember, the beam elements were not connected to the rest of the mesh. That caused the error. We went over a very important rule, and I'll stress it again. Always perform a normal modes analysis first. Make sure your model is properly connected. Once the eigenvectors or the mode shapes look okay, then perform your actual analysis. In this case, it was a statics analysis. So that's one very important rule. If this is your day one, do a normal modes analysis. Look at the mode shapes. Make sure the model has a common mode shape. Make sure nothing is disconnected. After that, we took a look at the post-processor web app. You can use Patran to look at some of the results. Alternatively, you can use the post-processor web app to look at your deflections, your beam forces, stresses. You can look at the failure indices, your apply stresses. And then at the very end, how do you perform a optimization? I wanted to keep it simple. I just wanted to optimize the number of applies and just minimize the mass. If you want to add some additional constraints, it's really simple. Here, let's go to constraints. Let's go ahead and define a displacement. I want to say that the Z component displacement for node 1917. Let's go ahead and look here. Let me step out of here. Let me go to the post-processor web app. Let's go ahead and look at where the maximum value is. It's on node 1917. So let's say here, for node 1917, the most deflection is maybe 1 millimeter as an example, and the max deflection is a positive 1 millimeter. So here I've selected one displacement. I go to the subcases section. I go ahead and assign my constraints. I go to the exporter and download this again, and then I can start my optimization again. So there you have it. Again, I know some of you, it might be your first day using Patran and MSC Nastran. For some of you, it might be more intense. You might be asked how to perform an optimization. I wanted to give you a good overview of everything you should expect when defining a complex model. Again, we went over Apex and how to create our geometry and mesh the geometry. We went over the use of Patran to define everything else, the materials, the loads, and so on and so on. We looked at the results in Patran. We also looked at the results in the post-processor web app. At the very end, we configured an optimization. Again, I recommend using the web app to do this. Other tools, some of their interfaces were developed 30, 20, 10 years ago. The web app is something you want to use if you want to make your life a little easier. If you're a student, you get access to the student edition of Apex, Patran, and MSC Nastran. Let's go ahead and figure that out. So student edition, Patran, Nastran. And then here we'll go ahead and go to this link. At this link, if you go to the very bottom, let's go ahead and ignore this cookie request. There's a button that says download. Click register here. Fill out the form. Upload your student ID. Click register, and then they'll get back to you in a few days. Also, the post-processor web app is free for any professional engineer, PhD researcher, professor, student. Post-processor web app is here for you to use for free, and the SOL 200 web app. There's also a free version of this tool available on the website, theengineeringlab.com. So if you go to this website, here at the top right hand corner, there are 2 buttons. Feel free to fill out that form, and then we'll go ahead and send you a link to access the software. We'll give you either a web link, or we'll give you an installer that you can download and install in your own company or your own university. Okay, with that, I'll stop here. And as always, thank you so much for watching.